Hello everyone. Today I'm just going to do a brief intro to optimization. There's a lot of examples and practice in your notes, and I will provide the solutions to all of those. But for now I just want to do the first problem. And in your classroom, so this blank set of notes plus the worked out solution to the guided examples. On Monday or Tuesday I will post the worked out solutions to the extra practice sets. So there's no textbook questions or anything, it's just all right here. I also will include the CDLI videos for this section. They go through the different types of questions when it comes to optimization, because optimization is a very broad term. You could be optimizing anything, and when it comes to optimization, it might mean you want the biggest or the smallest. Like if we're talking about cost of something, we might want the cheapest. If we're talking about the area of something, we might want the biggest. You've actually done these problems in the past. You did them in 2200, but you would have been looking for the vertex of a parabola. And how do we find the max or min values using calculus? Well, we use the derivative. So now we can expand optimization beyond parabolas. So we need an equation that we can take the derivative of, and that will provide us with the max or min values. So for this problem, it's an area problem, but perimeter problem could be handled similarly. The person wants to plant a rectangular garden along one side of this house, so this might sound familiar, with a fence on the other three sides. So if this is the house, and then we want a fence here, here, and here. And it says rectangular, but it could be a square. We don't know that for sure. So the key with this one is using variables or unknowns to set up your sketch and set up your information. So for example, we're used to using x's and y's, and that's fine, but I like to stick with letters or different letters that represent the situation. So let's say if this is width, and this is length, and you'll see why in a minute. And so I'm dealing with area. It says find the dimensions of the largest garden. Right, so it doesn't say the least amount of fencing or the most amount of fencing. We need largest garden, so that's area. So what we're trying to maximize is the overall formula. So area in this case would equal length times width. So we're looking for the maximum area. And in most measurement cases there's a constraint. Okay, so the constraint formula would mean, for example, we've only got 14 meters of fencing. So what kind of formula do we need to use to represent the length of fencing? Well, the formula for length when you're dealing with rectangles is perimeter. So what do we have? We got two W's and an L. So 2W plus L. Okay, so that's kind of all the setup. If you can do that in your head, great. I mean, it's just kind of a bookkeeping type thing here. We're trying to organize our thoughts. So what we want to do is maximize the objective formula, so the area formula, that's what I mean by the objective. And the maximum value will occur where the derivative equals 0. So we got to find the derivative and let it equal 0. The problem is we can't differentiate a function when it's in terms of two variables. We don't want to use implicit differentiation here. So we have to write our objective formula in terms of a single variable. That's why we need that second formula. In order to do this, we rearrange our constraint formula and substitute it into the objective formula. So the constraint formula, we know what the perimeter is. It should be 14 equals 2W plus L. So I can easily rearrange this one in terms of L. All I've got to do is get my 2W to the other side of the equal sign. And then I can swap out the L in the original. So what we're going to get our head around now, this unit with word problems, is we don't have to use x. We can differentiate with any variable. So the calculations here, if my constraint formula is written as 14 equals 2w plus L, then I know that 14 minus 2w equals L. So then what we would do is take that value here, so this equivalency, wherever we see L in our area formula, we can put in 14 minus 2w. So now area equals 14 minus 2w times w. So this is length times width. Then what we like to do when we're doing derivative is I don't want to use product rule. If it's an easy fix, I can just go 14w minus 2w squared. So what we're doing now is we're taking the derivative of the area formula with respect to w. It doesn't really matter what the variable is as long as it's the same variable. So a primed, in this case, the derivative of area would be 14 minus 4w. And then the max and min occurs when the derivative is 0. So now we let a prime equals 0. So that means the max will occur when we get 4w equals 14 and w will equal 3.5. Okay, so that gives me the max or the best width to maximize the area. We go back to our formula. If the width is 3.5, so the length, right, we can go back over here. The length is equal to 14 minus 2 times 3.5, which is 14 minus 7, which is 7. So based on these two answers, the area will equal, or the max area will equal 7 times 3.5, which is 24.5 meters squared. So I've put the answers in the bottom right corner of all these examples if you want to try them before you look at the solutions. But that's a max problem dealing with area. You've probably seen one like that before. In previous units you would have done the same thing, but when you get here you would have found the vertex. So the derivative calculation is a little bit easier. You don't have to worry about rearranging the form. Alright, so take a look at the optimization problems. Use the CDLI videos if you like, but ultimately this is a very popular application of derivatives. So have a great weekend. I'll post the rest of the answers to the practice and more practice problems on Monday. Your skill check will be on this stuff next week, and I'll let you know about all the extra material if you want to continue to get ready for your CPT in a few weeks. Bye for now.